Hello and welcome to this session on building secure IoT solutions with Azure Sphere. My name is Dave Glover. I'm a cloud developer advocate at Microsoft with a focus on the Internet of Things. It's also my great pleasure to introduce Peter McAlpine. Peter is the Operations Director at Divvy Parking. Now Divvy Parking are a Microsoft partner based here in Sydney, Australia. Now this session is going to mirror the content you'll find on my GitHub called the Azure Sphere Developer Learning Path. There you'll find more detail than I'm going to cover in this session, plus a series of hands-on labs. So please check out aka.ms/Azure Sphere Developer Learning Path. Now the agenda for this session is an introduction to Azure Sphere. Peter is going to talk about why they chose Azure Sphere as part of their overall secure parking solution. And following that, I'm going to do a demo of how to build an Azure Sphere application with Visual Studio. Now, IoT opens up enormous opportunities to really transform our lives, our communities, businesses, and even government, but it also invites enormous risks. Connectivity is a two-way street, and hackers are a creative and determined and cunning bunch, and they're constantly changing their tactics. And you may find that products that you brought to market aren't being used in the way in which you thought they might be. And really a day goes by without some sort of headline related to IoT security. Now this could be baby monitors or toys or vacuum cleaners turning on cameras and spying into families, heart pacemakers and cars being hijacked. The list is really quite endless, and none of us want to be building products that end up being used in ways that we had never intended. Next, I want to talk about approaches to mitigating security risks. Now I'm sure you appreciate that getting security right is complex, it's expensive, but more importantly, it's ongoing. And attack vectors are constantly changing. Now, Microsoft has a long history of building secure internet-connected systems and devices. Clearly, some of that has been checked, and we have learned a lot of lessons. And it's those lessons we're applying to Azure Sphere. Now, Microsoft in the industry has identified 7 properties required to build highly secure devices. Now, it's not my intention to go through all of these blow by blow. You'll see a link down the bottom, which is aka.ms/7properties. Do check that out to have a better understanding of the properties required for building highly secure devices. Now I'd like to introduce Azure Sphere. So Azure Sphere is made up of 3 components that together implement those 7 properties for highly secure devices. The first component is the Azure Sphere certified microcontrollers from our silicon partners. Now these are connected, crossover microcontrollers capable of running a high-level operating system, high-level apps, as well as real-time applications. The second component is the Azure Sphere operating system, where we will provide ongoing updates to ensure the platform is secure. And the third component is a cloud component called the Azure Sphere Security Service. And amongst other things, it's responsible for brokering trust, detecting emerging threats, renewing device security, and app reporting. Next, I want to talk about the hardware ecosystem. So MediaTek is the first partner to bring out an Azure Sphere certified microcontroller, but we've also made announcements with NXP and with Qualcomm. Secondly, there are 3 developer kits on the marketplace, and these are great for prototyping solutions. So Avnet have brought out their Azure Sphere starter kit, and it includes the sensors for temperature, for humidity, light. There's a gyro and accelerometer, and it's also extensible with Grove peripherals and micro-click boards. The second partner to bring out Azure developer kits is Seed Studio, and they brought out 2. They brought out the original reference design board for Azure Sphere, and also they've recently introduced their mini board. Now both of these boards are also extensible with Grove peripherals. Now if you get to the point where you want to build a bespoke solution, then there are Azure Sphere modules, and these will speed up your time to market as they're pre-certified. So there are modules there from USI, from Avnet, and from AI-Link. And finally there are Guardian modules, and these are pre-packaged or off-the-shelf solutions for Azure Sphere where you want to go and internet enable existing equipment. So for example, Divvy Parking are internet enabling boom gates for their secure parking solution. Starbucks use the Avnet Guardian modules to go and internet enable their coffee machines. and QIO have recently brought out a secure cellular solution. So now I'd like to hand over to Peter, who's going to talk a bit about why Divvy Parking chose the Azure Sphere to be part of their overall secure parking solution. So Peter, welcome.
Thank you, Dave. Welcome everyone. My name is Peter McAlpine and I'm Operations Director here at Divvy Parking. At Divvy, we've built an enterprise-grade parking management solution with features for owners, tenants and the public, all built on Azure platform that provides us with the security and scalability that is demanded these days. This helps us securely provide parking to over 30,000 people a month, plus provide insights from all that collected data. When we come to the installation in the buildings, we come across very old school technology. Some even predates the internet. WAN protocol, for example, which is used in many swipe cards, came from the 1980s and is still used today. Divvy needs to work with this equipment and run control cables between all this across car parks, maybe up to 50-metre cable runs. But replacing this with a wireless device from a local electronics store probably is just a backwards step. As Dave mentioned from the fish tank scenario where somebody could just sit there and wirelessly hack away and nobody would notice. Whereas with conduit you could see them pulling apart and hacking into cables. Internet of Things, it all sounds really cool. And there's lots of things on the market, some have internet even. But when you think about the big data, analytics, automation and security, I'm not convinced that some of these things should wear the IoT nameplate. And that was the problem we faced when looking for a solution of where we went next with our product. Divvy didn't want to add another disparate technology with all the issues that brought. We just wanted a device that easily connected to Azure with a couple of built-in relays and inputs ready for connection. At that time, Azure Sphere had just been released for developers. It has high levels of inbuilt security, an easy SDK to make the connectivity to IoT hub really straightforward, and it just becomes an extension to the existing Azure infrastructure that my team already know and loves. Perhaps you could replicate some of this on a Raspberry Pi, but not to this level and scale. The end result, I now have a device that is easy to manufacture. My install has less cabling, which means less cost and complexity, and monitoring and maintenance are far simpler as it's all just straight built into our Azure ecosystem platform. Which brings me to my next slide. Azure Sphere is really just an extension of the Microsoft Azure ecosystem. It made it an easy decision for Divvy to select this path and start making smart, secure buildings a reality. Imagine the future of smart cities, smart buildings. Currently, city buildings are probably sitting empty, hopefully not for much longer, but I suspect the aircon and the lights are still on during the day. What if a facilities manager could log into a portal and check this? He could then remotely shut down unnecessary electrical equipment. He could go further and set up alerts on the building entry and workflows to bring equipment back online automatically, all without leaving the safety of his home. Collaboration is a big part of making this world a better place. As shown in this slide, the Divvy controller is just a piece of that puzzle, and we designed it exactly that way to be a piece of our puzzle, or even a piece of your puzzle. If that might be you, get in touch and we can share some ideas. If you want to know more about making your parking more efficient or Azure Sphere, please get in touch. Thank you for listening. Back to you, Dave.
Hey, thank you very much, Peter. Really appreciate you taking time to talk to us about how Divvy Parking are using Azure Sphere as part of your overall secure parking solution. Okay, so I'm going to switch gears now and talk a bit about building applications for Azure Sphere. So the first thing is you can go and build applications from Windows 10 Anniversary Edition or better, and from Ubuntu 18.04. The developer tools are free. Now on Windows, I would recommend you use Visual Studio 2019, but you can also use Visual Studio Code or the command line if you want to integrate into existing tool sets. On Ubuntu, you can use Visual Studio Code or the command line. Now there's a very powerful integrated debugging environment both for high-level applications and for real-time applications. In the demo I'm going to do, it's going to be high-level applications. So the demo I'm going to step us all through is using the AVNet Azure Sphere Starter Kit. Now this board I've enabled for debugging. So what that means is I've claimed the board into a tenant, I've logged into that tenant, I have development rights for this board inside that tenant, and I've enabled this board for debugging. So the key point I want to get across is I could not just pick up a random Azure Sphere board and just start developing on it. I need to have authenticated with that board and have developer rights. So the demo I'm going to do is using Visual Studio 2019. I'm going to be using Azure IoT Hub, and I'm going to be debugging a high-level application. So the demo I'm going to step through is a subset of the demos and hands-on labs that you will find in the Azure Sphere developer learning path. And a quick couple of concepts. So the Azure Sphere that I'm going to be using has the MediaTek MT3620 on it, microcontroller. Now that microcontroller is a multi-core microcontroller, and there are 5 cores altogether. 3 of those cores can be used to run your applications. So you can run, and those cores are highlighted in red. So there are 2 ARM Cortex M4 cores that you can run real-time applications, so things like FreeRTOS or Azure RTOS or bare metal applications. They would typically be applications where you need very precise timing or highly deterministic timing. The other core that you can go and build applications on is the Cortex A7. Now that is for running high-level applications. So that is running the operating system on that core, plus you can run your own high-level applications. Now the other 2 cores is a core in there for networking, and there's another core in there responsible for the security subsystem. Plus of course there's flash storage and there's memory. But there are 5 cores, 3 of which you can build applications, run applications on. And just as a bit of an intro to the operating system architecture, I just want to point out a couple of things. So in this demonstration, I'm going to be building an application which is going onto the Cortex A7 core. So that core is also running the custom Linux kernel, which has been built with Yocto. There are some number of operating system services running on that same core. So there are authentication services, over-the-air update services, application management services, and network management. And on top of that, I can go and build a POSIX application that will run on this as a high-level application. So what this means is that this core is running operating system services, networking service, authentication services, etc. So the operating system is what's called measured boot or a secure boot environment. So all components, the components will only load if they have been certified and verified. And that is the same for the other components in the operating system, including your application. Now, the applications you're going to put on the Cortex A7 are applications which aren't so timing sensitive, because clearly there's a lot of things happening on that core. The core where you want to put things that are more timing sensitive are on the Cortex M4 cores. And applications running on those Cortex M4 cores can communicate with the Cortex A7, and those applications on the Cortex 7 could then basically relay the information that's coming from the applications running on the Cortex M4. So what I want to point out here is that the applications running on the Cortex M4 cannot directly communicate with any network service for security reasons. Okay, so this application, just pointing out, this is the AVNet board. I'm building an application for the A7. It's going to be talking to Azure IoT Hub, and I'm going to be using the Azure provisioning service to basically enable that application, to provision that application. And what that effectively is going to do is provide the device a connection string for Azure IoT Hub. Now, device provisioning service does a lot of things. It does device provisioning and device balancing and load balancing of IoT hubs and things like that. But in this case, super simple. I've just got one device provisioning service, and its role is to provide a connection string to that Azure Sphere board and to enable that board to start communicating with Azure IoT Hub. Now, I'm going to show you the app manifest. So by default, on the Azure Sphere, everything is locked down by default, and you have to whitelist all the resources that you want to use. It's part of the overall security regime within Azure Sphere. So there's an app manifest, and in that I need to whitelist peripherals that I want to use. So for example, GPIO or I2C or SPI or others, pulse width or whatever it is. As well, so what's not on this is I also need to whitelist network endpoints. Next, we're going to fire up Visual Studio to give you a sense of how to go and build an application for an Azure Sphere. And I'm also going to switch cameras. So down at the bottom right-hand corner, you'll see the Avnet Azure Sphere Starter Kit. So you can see I've opened up this project called Hello World Avnet. Now you'll find this sample in the Azure Sphere Developer Kit. And as I said before, this is a cut-down version of the labs that you'll find in the Developer Learning Path. So I'm going to open up main.c, and you'll see that there is a set of include files. The first half a dozen or so include files are from the Azure Sphere Developer Learning Path, and they will help you build much cleaner, simpler code for connecting up to Azure IoT Hub and doing things like sending messages and managing device twins and direct methods. The rest of the include files there are the standard ones that come with Azure Sphere. So you can see there are things in there, for example, handling GPIO or logging or power management or Booleans for that matter. And I'll go into the rest of the code in a bit more detail shortly. What I want to do now is jump across to this file called app_manifest. Now, as I mentioned, the Azure Sphere and the applications are locked down by default. So an Azure Sphere has access to no resources until you whitelist them. So what I'm going to do is whitelist some peripherals, and I'm just going to copy and paste those over here. So I'm going to just copy those over here and paste them into the app manifest.json file. So what I'm doing here is I'm whitelisting GPIO, so I'm whitelisting the relay, and that lives on GPIO 0, and I'll talk about that in a bit more detail shortly. I'm also whitelisting access to the I2C bus as well as the ADC, so the analog to digital converter. Next thing I need to do is whitelist the network endpoints that this application is going to be talking to. And we'll just copy those and paste them in. So these network endpoints, there are 3 of them. So 2 of them are to do with the device provisioning service. So one is the global device provisioning service endpoint, and the other one is specific to my device provisioning service. And the third one down here is the endpoint for my IoT hub. And I'm going to talk about those in more detail. In fact, no, I'll just jump across and I'll show you where that came from. So what I've done here is I've just switched across to the Azure portal. And in there you can see I've got a demo resource group called Azure Sphere Demo. And in here I've got 2 services. And I've got a device provisioning service and I've got an IoT hub. So if I go and click on the device provisioning service, you'll see over here that these are the endpoints that I need to whitelist. So I need to whitelist the service point for this device provisioning service, and I need to whitelist the global endpoint for the device provisioning service. Now the other endpoint, if you remember, I mentioned you've got to whitelist the network endpoint for your IoT hub, and you'll see that up there. So I'm just going to jump back to Visual Studio. So next thing I'm going to do is just go into the code. So hopefully it's pretty clear. The device is locked down completely by default, and you need to whitelist resources. Okay, so next we're going to open up main.c to add some code to the project. So I'm going to scroll down here, and I'm going to jump across to GitHub. And on GitHub, inside the Azure Developer Learning Path, you'll see that there's a Hello World example, which is what I'm using for this demonstration. And the first thing we're going to do is add in some code which is going to be responsible for streaming telemetry to Azure IoT Hub. So I'm going to paste this code in. And the first thing I'm going to talk about is an event timer. So an event timer is a data structure here which just basically simplifies setting up timers. you can set the period for this timer. So in this case, the timer is going to fire every 5 seconds and 0 nanoseconds. The timer has a name, just useful for problem resolution. And every time that timer fires, this handler will be called. So the read sensor handler will be called. And you can see the implementation of this read sensor handler. So the first few lines here are just to do with removing this event from the event queue. The second part of this code here is responsible for reading the telemetry from the AVNet Azure Sphere board. I'm going to log it and I'm going to send that message to Azure Sphere. So it's going to do the read, and in this message buffer, it will return back a JSON formatted string with the telemetry. I'm then going to log this, and you'll see inside Visual Studio you can look at the log debugging output window, which I'll show shortly. And send message is responsible for establishing a connection to Azure IoT Hub and sending the message. Okay, so the next bit of code I'm going to add in. So this code is responsible for doing something called managing device twins. Now I'm going to go into a bit more what device twins are shortly. So I've just copied that code. I'm going to jump back to Visual Studio and I'm going to add that code into the application. So the first part of this code, again, it's a declaration of a peripheral. And the peripheral is called LED1. And there, again, it's a data structure which describes this peripheral. So the relay pin that's using, if I hover over relay, you can see it's using the AVNet MT3620 and it's sitting on GPIO 0. The direction is output, which is fine for something like an LED or a relay. I can set it to input if I want to go and measure if a button had been pressed, for example. I can define the initial state, and this is the C function that will be called to initialize and open this GPIO port, a pin. The second thing that gets declared is what's called a device twin binding. And I'm going to talk a bit more about what device twins are shortly, but just keep in mind that this again is a C structure, and it defines a twin property name, and that name is relay1. Also defines a type. So this is of type Boolean. So the message I'm going to get back from Azure IoT Hub is either going to be true or false. And that is going to correspond to being on or off. So the relay will be on for true and off for false. And when I receive a device twin message, which has a device twin property name of relay1, this handler will be called. So the handler LED1 control handler will be called. When it is called, the device twin binding will be passed. And as part of that, there is a property in there called twin state. And what's happening here is that this is being cast to a Boolean. So again, you're going to get true or false. And obviously, if it's true, what I'm going to do is turn the GPIO on. And if it's false, I'm going to turn the GPIO off. And that's going to correspond to true or false. One more bit of code that I need to copy in. So what I need to do is initialize those peripherals, the timers, and the device twins that I've just copied into that code. So I'm just going to come down here and replace this code. Now, the Azure Sphere Developer Learning Path has some kind of convenience mechanisms for dealing with timers, peripherals, device twin bindings, and direct methods. Now you can see in here, I've got a timer set. Now this has a reference to the read sensor timer. So I'm passing in the address of that object. And then what I'm going to do in this function down here, which is called init peripherals and handlers, you'll see that if I click on the timer set, you'll see that there is a function that is called start timer set. And it is going to be passed in this timer set. So the idea behind this will open all timers that have been referenced inside that timer set. Exactly the same deal for peripherals. So I've only got one peripheral object that's been referenced in this timer set, but clearly I could have multiple, and most likely I would. The same applies for timers. It's highly likely you'd have a lot of timers running. And device twin binding sets is exactly the same idea. I'm passing in a reference to the device twin declaration, and you can see that up here. And again, the same principle applies. You'll find init, peripherals, and handlers. You'll see that device twins get initialized with a call to open device twin set. Now I'll just step through the rest of this code. So I've just introduced init, peripherals, and handlers, which is responsible for basically setting up the environment. There is a corresponding close peripherals and handlers, and surprise, surprise, that's going to stop the timers, close the cloud to device, close peripherals, and close device twins. And all good C or all good main.c applications will obviously have a main entry point. And you can see in here, there's a call to init peripherals and handlers to initialize everything. The application will sit inside an event loop, and when it receives events, timer events most likely, it will call the handlers for those timers. And for whatever reason, should that timer loop close, then device peripherals and handlers will be called to close all the resources that this application is using. So if you could look at the top of the screen, what I'm going to do now is set the build configuration. So I'm going to select ARM debug, and then I need to select the startup item. The startup item is GDB debugger HL core. You remember HL stands for high level. It's the high level core on the Azure Sphere, which is the Cortex A7 core. So I'll click start, and what that's going to do is going to compile the code. It's going to copy the code across to the Azure Sphere. Then it's going to copy across the debug symbols, and then it's going to attach the debugger. So while that's starting up, I'm just going to move the device camera so we can see what's going on in the output window. So the application is starting up, and you can see now in the output window down the bottom right hand corner of the screen. So you can see I've got output tab selected, and on the drop down I've got device output. And if you look there closely, you'll see that there goes the JSON formatted string with a telemetry in it. Now that telemetry is coming from this function here called read sensor handler. And you'll see down here, I've got log debug, and that's what's writing that information to the output window. Okay, so what we're going to do now is just change gears a bit, and we're going to switch over to the Azure portal. So remember, I've got two services up here. I've got the device provisioning service, and I've got Azure IoT Hub. Now, before I do that, we're just going to fire up the Cloud Shell. So the Cloud Shell here, I've already preloaded it, and you can see I can either use Bash or PowerShell as my command shells. We'll just maximize that, and we'll go back in command history. What I'm going to do now is start up the Azure command line tool, and the command I'm passing through is the AZ IoT Hub monitor events. And you can see this is displaying the events that are coming from the device. And yes, you can see up there goes that JSON formatted string again. Okay, so hopefully that gives you a bit of an idea how you can check out the telemetry and just make sure things are working as you might hope. So what we're going to do now is go into IoT Hub, and I'm just going to scroll down here and select IoT devices. And there's only one device in this hub, and this is the demonstration device that we've got here. And what I'm going to do is select device twins. Now, I said before that I'd discuss more about device twins later on in the demo, and here we are. So the first thing is a couple of concepts about device twins. So the first thing, a device twin is a JSON document that is managed by IoT Hub, and there is a JSON document for each device the IoT Hub is managing. Now, there are two core concepts that you need to understand. The first thing is desired state. So the idea is that your application can go and set the desired state of in the JSON document, and then IoT Hub will send a desired state message down to the device, and the device will action that request, and then what it will do is that it will send back a reported state. So in this JSON document, there is both the desired state that you set from your application, and there's a reported state back from the device. And you can see that I've got a device twin property named relay1. You saw that in the code, and the current state for that is false. So the advantage of this is that you've now got a reflection of the state of the device up in the cloud. And there is a API and there's a query language that you can query to say, find me all devices where relay 1 is set to false. And maybe your application wants to set that to true, and maybe turn on all the lights on the factory floor, for example. So what I'm going to do now is we're going to pop back to Visual Studio, and I'm going to select and put in a debug breakpoint. So this is the handler for the device twin, and that's the implementation there. We're just going to put a breakpoint in that code. So when this code executes, the code will halt at this breakpoint. Jump back to the portal, and what I'm going to do now is I'm going to set the desired value for this property to be true. Now you remember, I'm editing the raw JSON document. You would clearly build an application which would use the APIs to go and manipulate this document. So I'm going to set, but this is just great for testing. So I'm going to save that, and we just minimize that down, and in a moment that breakpoint will be hit on the device. So you can see that message has been sent down from IoT Hub down to the device, and we're now going to step through that. And remember, device twin will have the state that was as part of that message, and then I'm basically casting that to a Boolean. And we'll just press F10 to step through this code, and you'll see that the LED goes on, and we'll just go F5 and that to continue the application running. And now what I'm going to do is pop back to the Azure portal, and we'll do a refresh. So remember, down here for that reported state, the relay was false. If I hit refresh, voila, the reported state is now true. And obviously that works. If we go and set that to false and save that, exactly the same principle. This time we're going to turn the LED off, and if we just step through the code, and that'll turn the LED off. F5 to continue. Jump back to the portal and do a refresh, and we'll scroll down to the reported section, and you can now see that the reported state for that variable or that property on the device is now false. So I hope that gives you a bit of an understanding of what you can do around building applications. So we'll just jump back across to the Visual Studio. So we talked about setting up timers. So we'll just go and find the timer. So we had the timer there. We had the handler for the timer. So every 5 seconds, this handler is going to be called, and it's going to read the telemetry from the device and then send it up to IoT Hub. We defined a peripheral. In this case, the peripheral is attached to an LED, so attached to a relay, which I've attached to a torch to, and that's for output. And then remember, we did a device twin, and the device twin binding. This was a cloud to device twin binding, and the device twin property name is relay1. By the way, you could also do a device to cloud device twin binding, and you'll find more information about that in the Azure Sphere Developer Learning Path. And you can see this was the handler, and the handler gets called and a message gets received, a device twin message gets received, and in this case I'm simply going to toggle a light on or off, and then the device will automatically report back the current state or the new state of that property. Remember, there were the sets down here. Think of the sets as sets or collections or whatever you wanted to call them, but I've chosen sets because it was a bit more succinct. These are just arrays. These will manage the initialization of things like timers. So you can have multiple timers. The same deal for peripherals sets, just passing in a reference to the peripherals that you've defined. And the same thing is for device twin sets. You're just passing in a reference to all the device twins that you've set, and they will be opened and initialized in the init peripherals and handlers. Okay, so what we're going to do now is just jump back to the slides to finish the session. So what I'd like to do now is just highlight some resources available for Azure Sphere. So a great place to keep an eye on is the Internet of Things technical community. So you can see the URL there. Check out the Azure Sphere documentation. You'll find information on Azure Sphere pricing, also the official docs for getting started for Azure Sphere, as well as a link down there for Azure Sphere support. Please do check out the Azure Sphere Developer Learning Path. The demonstration I gave you was based on the libraries that you'll find inside that learning path. They're all open source. You're free to use those libraries on your own projects as well. The link there to the Developer Learning Path is aka.ms/Azure Sphere Developer Learning Path. Please do follow me on Twitter. And if you don't use Twitter, then please follow me on GitHub. So you can find me on GitHub at Gloveboxes and on Twitter at dglover. So thank you very much. And please, as I said, please follow me. If you have any questions, please ask me on either Twitter or GitHub. Thank you very much.